I wanted to give a sense of what is, what industry already knows, and then, some of the hard problems where we need to still think a little bit about, beyond the hype that we hear from the media. So that's why I'm calling it What's Special About GeoAI. Also, I wanted to share this MIT Press Essential Knowledge Series. One of my book just came out, which tries to present a lot of this information for a broad audience in easy to understand manner. So thank you again for a warm introduction, Harsha, and giving me the floor. Also to share my background, we do have a number of projects from different federal agencies, and we have learned a lot about this space by actually trying to solve real problems with real clients. So we all know spatial has been a major revolution in terms of GPS, spatial big data, which is very valuable, and now people believe remote sensing can also go, even bigger than what GPS and spatial big data so far has been. Right? We have also talked about AI. It has had its ups and downs, different AI winters, but certainly it's again on its swing up. And it has many ideas. The recent enthusiasm is largely because of deep learning. Right? So we can think about, what does it give us in geospatial world, which has, again, a very rich history. And one of the area which probably many speakers have already said is that it can start to automate some of the things in map making. To give you a dramatic example, US National Wetland Inventory took about $400 million over 40 years in last century. And clearly we cannot afford to wait that long to update these maps as climate change and so on, they need it, right? So machine learning people have been using, we heard about NDVI and other things, and I will show that. But we can say what else, what value we add from deep learning and so on. Then there are other problems like inverse geo problem, which are very niche. And I'm not sure if industry has been looking at it carefully, but it's very important societally. And the related problem is geo content-based querying. But then I will probably share that not everything is really pretty. I mean, there are lots of things that AI needs to learn as well from our space and other places. Right? So let's think about cheaper, faster, bigger map. If I were in the room, I would have asked you to raise a hand of how many of you know about GeoGlam. So every 2 weeks, they produce the crop report for the world for 4 major crops using remote sensing, right? So this wouldn't be possible without machine learning. Right? And this is a federated system. Each country collects its own data. They run machine learning. They do some ground truth verification and report it. This is used by every single government in the world because they don't want to repeat Arab Spring. This is used by every food company. And this wouldn't be possible doing the things the way we did for, in last century. Right? But things are getting better. Even if you think about other problems like disaster relief, where time constraints are even more limited, we need to make things better, right? So even the traditional AI, which was used in last century, where we kind of did feature selection, step 2, and then did some kind of a classification, we probably do not have even time for that. And what people are now doing is to compress these 2 steps in a single step. And that is the excitement of deep learning, right? So you may argue that remote sensing has designed these really nice, well thought out features like NDVI. So what's the point of making machine learn it again, right? So the limitations of NDVI. Right? So NDVI tells you overall plant health, but it cannot help you diagnose the reason. Is it a particular insect or nutrient deficiency and things like that? So we have a choice. We can again spend another 50 years trying to figure out indexes for all of these conditions, or we can let the machine try and build it from the examples, right? But you can turn around and see, well, does NDVI still give me any value? And it does. And you can look at our paper. If you do have good hand-constructed features which are lab validated, they can help deep learning, use less, fewer number of samples or fewer cycles, right? So these are still open debates, but we think it's good to combine good ideas from both places and not follow the, really the ludicrous presumption that deep learning neural network can learn everything, right? They need help, okay? And we should help them. Beyond that, people are also making maps of geo objects. So the old computer vision workflow was very clunky. You did edge detection and then segmentation, and every step added error. And now, as you know, deep learning is kind of a one-shot. It's going through multiple steps in one case, and it has been very successful in many things. For example, I'm showing detection of vehicles in a parking lot, right? This could be used by retailers to know, the health of their competition or their own stores, Or, this could be used by trucking companies to know how many trucks are in a building, right? And these things work pretty well. This is showing you some results from YOLO to detect trucks, cars, houses, and so on. And probably industry is getting into it as well. There is a very successful company trying to estimate world petroleum reserves by looking at the imagery of the storage, because they have floating roof, and the shadows tell you how much oil is in the storage. Great. So let's go to a different problem. Map making everybody does, so it's probably not that great a news, but you can do other things. And I will mention two problems which are broadly inverse problems, which is the crux of AI, right? So here is one. Suppose we are worried about GPS jamming and spoofing. So this aircraft from New Orleans to Minneapolis is flying along Mississippi River, and they want to do visual navigation, and they see something like this below. So can we tell where we are on this Mississippi River? If Dr. Chawla is here, he might recognize this place. Okay. But anyway, that many places have very unique scenario. This is Minneapolis. You can see the Vikings football stadium or Gopher football stadium, St. Anthony Falls, and things like that. And we can do that for many, many places in the world. And here are some others. I will pause here to see if you recognize any of these images. Again, Dr. Chawla comes from one of the places. It is very near one of the image here. But you may have other people around the world who might recognize other of these. So again, you can imagine, given an image, we want to know where it is. And that's really an inverse problem, very much like in computer vision. Given an image, we want to know whether it's a cat or a dog and so on. Now, this actually is not a hypothetical problem. You have some real application. And here is one. This was released by a Russian Ministry of Defense saying that they bombed a particular, insurgent site in Syria. Right? And but actually, if you match it with Google Earth, it turns out to be a grain storage facility 150 kilometers away, right? People can create these kind of fake images and video, and you see that on social media all the time. And we need to fact check the geoimagery. And that's a great AI problem. And this will be worth, industry's chops to see if they can figure it out. And there are other problems. AI, many people think that they sometimes climb a tree and they claim that they are on the way to moon. And we need to watch out for those things, because if you have a lawsuit and your jury is not going to believe your hype, they would want to understand what you did and why you did it, right? So there are a lot of them, many, many open problems. And, there are many big agencies which are playing in that space. So DARPA, which many people believe always addresses hard problems, they have been trying it to detect fracking, illegal fishing, and crop health from satellite imagery. IARPA started a new one where they actually want to look at a sequence of satellite imagery to understand construction and classify stages. They even want to look underground. Right? So American AI initiative actually acknowledges that, and they say, look, analyzing spatial temporal data sets is very, very hard. AI, doesn't really do very well there, and you need to have more research in this area. Here is a very simple question. A lot of you may be very excited about deep learning and convolutional neural network. Have you ever thought about, from spatial perspective, does it really address all the challenges in spatial data? So I will pause here 30 seconds and let you try to answer this question. Okay. What you may realize is CNN just learned spatial autocorrelation, okay, after waiting many, many years. They could have come to GIS people and learned spatial autocorrelation around Second World War, but they waited till they found it in the biology. They still don't know how to deal with heterogeneity, edge effect, and high cost of spurious missed pattern. And you can look at one of our recent papers where we have generalized neural networks to deal with these things, right? So AI is, still learning, and we should help them learn. Here is another one. You throw a little noise at all these deep learning and CNN, and all the hype comes to a complete pause. And I will just show you here. Here is a DB scan clustering, and in the noise, it's finding clusters, all the colors, right? So one of our recent papers, we basically tell them, how to deal with noise, and we can just throw out the noise and make it robust. Try to think about how you can do that to CNN. That's very, very prone to noise. Right? And other things, even their sensors are so, I would say limited. How many of you know that self-driving car is based on, right, RGB sensors and LiDAR? And you just heard Uber got out of that business. Their performance was so poor. And here is a news article, as soon as it starts raining, any bad weather, the self-driving cars cannot go anywhere. Now, our space knows a lot more sensors like hyperspectral and stuff of that kind. And it is the time we go and help AI, not just looking for AI to help us, And that can make AI much better. And there are many other opportunities. Here is something very, very simple. Have you ever asked Google the distance between New Delhi and India or Washington, D.C. and US? And look at the answer. I mean, they don't even know that spatial things can be polygons, right? Everything is a point to them because they don't know much spatial. And this is a place we can go and help the Siri and Google and Alexa and all the AI hotshots, so-called hotshots, to get better on geospatial things, right? So again, there are research and so on. So this is the big summary. Spatial data is, as big a revolution as AI, right? But of course, AI can help us do something, speed up our map making. But at the same time, we can help AI mature and learn about richer spatial data sets, how to deal with noise, how to deal with heterogeneity, and so on. So my basic ask is, let's join our hands and bring the strength of two sides together. And also, whenever we talk about AI or data science, we make sure we teach geospatial to those folks so that, they also grow up and they solve some societally important problems. So with this, I will stop my talk and just show you, if you were more interested in this topic, here are some resources. And you can see a lot of societal example and simple stories in this book from MIT Press.
I'll just say a few words about the work that we're doing in QCRI. And hopefully, that'll give you a perspective of, I won't, share slides. So basically, Shashi mentioned, Dr. Shekhar mentioned about the geospatial work. And, we've been using, spatial techniques. In particular, we've been using deep learning quite a bit. And let me set you the context. In Doha, which is the capital of Qatar, which is a small country in the Arabian Peninsula, there's the FIFA World Cup in 2022. And as part of that, there's a lot of construction going on. A lot of new roads are coming up. And one thing we observed is that Google Maps, for example, and other mapping apps don't work very well in this part of in Doha because there's so much transition happening about the road infrastructure. So we started working on trying to do, can we use, more advances in deep learning to do map inference. So first we thought, okay, what we'll do is we'll try and collect GPS data from taxis, and we'll try and use GPS data to infer the road network. And then we also started using satellite imagery. And when we started looking at the literature, we sort of observed that a lot of the work in deep learning was essentially about object detection, but also in the context of map inference, a lot about pixel classification. So people would take a satellite imagery, for example, and say, okay, this pixel belongs to a road, this pixel doesn't belong to a road. And a lot of the post-processing was still rule-based. So how do you actually extract the topology of the road network from the pixel level classification? So we said, okay, is there a way that post-processing, which was a lot of rule-based and sort of manual, could we actually apply modern machine learning techniques and deep learning techniques to actually extract the topology directly from the satellite imagery? So essentially, if you go and look back at the literature in spatial data science or GIS or even remote sensing, there's always this duality in spatial computing, or in GIS. There's a field view, which is very raster based, and there is what's called a vector view, which is based on points, line, and polygons. And it's often very difficult to reconcile the two views. So, for example, there are languages like map algebra about querying field level, field type data, field representations, while there is extensions of SQL and OpenGIS, formalization to query the vector form of information, like point, lines, and queries. So what we were able to do using deep learning was a different sort of modified approach, not off the shelf kind of approach, was to essentially take a satellite imagery and directly extract the vector map, and that vector map is now being is the basis of many other techniques that we are using to build upon that. For example, now we can use that same technology to extract the type of the road. For example, on one, suppose you have a road and you want to figure out meta-level information like the type of the surface, the number of lanes, and essentially we're able to use the same ideas to do that. We also are able to do some form of change detection. So the point I want to make is that, that to solve real geospatial problems, you really have to look at the problem, of course, and adapt existing techniques, or start from existing techniques like neural networks and CNN, and try to solve the problems for that particular domain. So this mapping from a field view to like a raster view to a vector view is actually very core to GIS, to GeoAI, and that's what we that's you have to know that to be able to sort of to solve that problem. The other kind of work that we have been doing in Qatar is about one thing we observed here is that that the traffic signals are not properly calibrated. So sometimes you can be at a traffic signal for 4 minutes or 5 minutes, and even though they have good technology, the state-of-the-art technology, somehow the traffic signals were not coordinated. And we said, okay, is there a way we can use, again, data in combination with some machine learning to actually address the problem? And so we started exploring ideas of what's called reinforcement learning, and sometimes also called prescriptive learning, where the focus is not just about description or prediction. It's actually about prescription. About tell us how to do it, how to reduce, how to coordinate the traffic lights in order to reduce congestion. So that work, again, we started from the actual problem on hand, and then we tried to adapt, now mostly it is deep reinforcement learning techniques to address the problem. And in reinforcement learning, there is, as opposed to, so there's a sort of a cousin of reinforcement learning, you can say, in more traditional engineering is called control theory. But in control theory, you assume that the dynamics of the system are known. But of course, in a traffic setting, if you try to write down the dynamics in forms of equations, then they quickly become extremely complicated. And so we said, okay, we don't know the dynamics. Let's assume we don't know the dynamics of the system, but let's try to at least get feedback from the environment. And so it's a combination of getting feedback from the environment, and then also trying to respond to it, which essentially is how to do that formally, what reinforcement learning is about. So we were able to stitch a solution for traffic signal optimization. And one thing we didn't realize at that time was that even our focus initially was just on trying to ameliorate the traffic congestion in the city by coordinating the traffic lights better. The side effect was we actually were also able to demonstrate that this will actually lead to a reduction of CO2 emissions, because there'll be less congestion on the roads, and less delay on the cars will stop for a shorter time. There'll be more smooth flow of traffic, and therefore that will actually reduce carbon dioxide emissions. And so the good thing about working in Qatar is that we can get access to very good data. So in other places it might be more difficult. So for example, there's one taxi company in the city, and once we were able to approach them, we were able to get taxi data for all of Qatar, and that we thought was very, very very something which is almost unbelievable, that we have access to very fine-grained traffic taxi data from the whole country. Another sort of example of how we were able to leverage spatial data was, when with the onset of COVID, you have heard of all these models like SEIR models about susceptible, infectious, exposed, infectious, and removed. And when you look at sometimes country-level statistics, you think that the pandemic is spread uniformly across the country. Of course, that's not the case. In different parts of the country, the dynamics are different. The question is, how do we actually capture those dynamics? And we were able to, extract some information from the taxi data, create what's called origin-destination matrices, and actually incorporate that into the epidemiological models, and show that how the epidemic will spread, even though it's a small country, how it will spread into different parts of the country, which areas will likely to get affected most or more. And if we were to have some kind of a lockdown, should it be a blanket lockdown, or can it be a calibrated lockdown? So we were able to come up with some suggestions and recommendations that sort of really took spatial data into account. So again, it's always in some sense, I think Shashi also likes to use this word, use inspired. You start from a problem, you have to understand the problem in detail, and then you bring in all your machine learning tools to bear on it, and that's how, at least in Qatar, we are in QCRI, in Qatar Computing Research Institute, we are trying to address many practical problems that are at the intersection of, where we use modern machine learning techniques, but always driven in the end to solve the problem. So that's our way that we are trying to address problems in this domain here.
Listening or having listened to yesterday's and today's presentations, it was interesting to see in how many different aspects, capacity building, education, qualifications were coming up. So within this academic framework, in the second session for today, I'd like to bring up the brainware topic and to spend a few minutes on that. When I was looking to the title of Human Learning for Artificial Intelligence, so the brainware aspect for AI, over the last couple of minutes, I figured actually I could swap it around, and we could just as well talk about human intelligence fostering artificial learning. But that would be just one thought to take from here. So we all know, and we've seen numerous wonderful examples yesterday and today, that one of the key driving forces between the emergence and the increasing popularization of machine learning was just a flood of data we are facing. We have moved as a discipline, as the geospatial discipline, from a data poor to a data rich and beyond discipline. So we are facing such a flood of data which we couldn't really address with any other method. So that was one of the starting points, clearly. And then moving into the somewhat more narrow realm of geospatial AI, we have to make it clear that there is a clear distinction. Well, that we're working with spatially explicit data sets where either location or spatial relations, which might be geometrical or topological relations, help us to detect features, identify features, to recognize patterns among gazillions of points or lines, to explore the area of movement analysis, which, by the way, is one of my favorite aspects where we're looking at it. I was very happy to listen to the previous speaker to talk about the taxi OD analysis that actually we're very interested in exploring this a bit further from our perspective. Natural language processing is another aspect, and I'll actually finish with a few examples at the end of my short talk where I get back to these. Since quite some time, we have considered machine learning an integral part, it has become an integral part of the general spatial analytics toolset. What do we do with that toolset? We work in classification, clustering, which obviously is an inherently spatial process, and of course we look into prediction. There might be quite a few more, but for all of them, the challenge in education is how to make sure that students and learners have the prerequisites for mathematics and statistics, the computational skills. We just heard the recommendation to focus on Python in the previous talk, and of course the required domain knowledge, and I'll mention that domain knowledge a little bit better. So how, as a student, anyone who wants to get into the field, who wants to enhance their qualifications in the field of GeoAI, how do we get our driver's license in a way? Essentially, what are skills and competencies needed to find out which methods are the adequate ones, how to interpret the results, and even more validate the results. And that works in a multifaceted field. Of course, spatial thinking has already been mentioned today. It's a prerequisite for going any deeper into GeoAI and spatial ML. Then there is a methodology area. Statistics would be a very broad term for that. And then there is the computing field. And all of that is embedded in what I already had mentioned as the domains knowledge. So how do we figure that into educational ventures? How do we qualify people to answer questions like this one? The question looking at the satellite image and trying to answer the question, how many people are living there now? How can we get a reasonable estimate for, like, in such an urban environment? Or one of the areas we've been working with for quite a few years with an organization called Médecins Sans Frontières, Doctors Without Borders, where we look at the demographics, at the day-to-day change in the population in refugee camps. How do we extract like 1 million buildings from a satellite image, high-resolution satellite image, and repeat the process after a few days, because those populations in those camps were quite quickly. So how can people be qualified to work in that area? So as we are all aware, there is lots of different formats for learning. Like, we pretty regularly offer short intensive programs, summer schools, and work with people who come from a range of related spatial disciplines, already having prior knowledge. My favorite format has become the MOOCs, the Massive Open Online Courses, because it's just wonderful how easy it is to reach out to 10,000s of people and to get them started into a field like ours. So I really want to call out this one MOOC I'm putting on this slide right here. And of course, we all in academia are working and thinking about and working towards how to infuse these competences of spatial AI and machine learning into more or less traditional educational programs, are facing the alternative to go full data science, which would be one other direction to go. Quite a few years back, data science has been identified as the sexiest job of the 21st century. And this nice couple is facing a couple of different areas in the math and statistics, programming, databases, then of course soft skills, domain knowledge, communication and visualization. And well, it's quite an optimistic view at the beginning of a century to make a prediction in our fast-moving environment that this would be the job of the 21st century. There might be other technologies coming forward, and It might not be the give and take all, but still, our debate is on spatial data science. So when I was looking at this slide, my first observation was, where did the girl go? So all of a sudden, is geospatial more male than spatial data science? I don't hope so. Maybe it was just a matter of space right here. But the qualifications listed here are quite, well, obviously relevant. The spatial skills, they are quite technical, like photogrammetry, geodesy, cartography. I would replace cartography with visual or geovisual communication, and I'm missing altogether the spatial thinking stuff here. But I'm only pointing to these fields because that's part of the discussion we as an academic field, we as educators in our discipline are conducting today. So like data science as such went ahead actually quite a few years ago with a body of knowledge, so a curriculum framework helping with designing and developing programs. And luckily, the spatial data science field was following suit. And if we go out there and look around, then we can see there's quite a few programs in spatial data science being offered and have established themselves well over the last couple of years. There's actually one common denominator here. They are all graduate programs, and that's actually an observation worthwhile thinking about, because to move straight into data science without building on the experience, the problem awareness from any domain, maybe is not the best of ideas. We might turn people out who are technical experts chasing down suitable problems to tackle with what their skills are. But in any case, spatial ML is one important tool set. But most importantly, what I would really focus on right here is we talk about transversal competencies. So we have to step out from the silos. There's a lot of spatial disciplines, lots of disciplines out there where people are not even aware that they are spatial, explicitly spatial. And with this, I would just like to conclude with, I mentioned natural language processing right at the outset, with a few examples, like huge amounts of data go into social media, Twitter and other posts, and they come in natural language, and we maybe want to extract emotions, located emotions, because they tell us something about how people feel in different places, and we might think about why they feel differently in different places. Or maybe looking at an example like this one, where we explore Corona COVID-related tweets across the country and how that evolves over time. And of course, these data come in all the time, so we might maybe want to analyze them dynamically. This is an example from the first phase of the refugee crisis in Europe a couple of years ago. And again, you cannot just have mobile phones moving around. You need to analyze the messages and try to extract semantics in order to have knowledge derived from that which supports decisions. Yeah, with those examples, I'd like just to finish up my discussion of how do we enhance the human intelligence, which facilitates artificial learning. And thanks for the invite to today's panel, and I'm looking forward to discussions and questions. Thank you.
One of the key things that we see, the question I would like to ask is that commercialization of research remains a key challenge in the geospatial industry. So can you provide some success examples or success stories from the research work you're involved in, and how this transformed into commercial utilization specific to the AI use cases?
The AI work is, I think more recent, but I can certainly share. I don't know how many of you have heard of UMN Map Server. In '96, this was 10 years before Google even thought about doing it. We had a very successful open source software to publish satellite imagery and do all kinds of very fancy analysis of how crop health, NDVI changes over the season, right? There are still 30,000 installations worldwide. NASA Worldwind is actually built around it for scientific work, and it's much richer than what you see on Google Earth or AWS Earth and so on, right? There were companies which were supporting it, right? Because we didn't have the manpower to go and help every user. There were very, very active groups, and it ultimately spun off and became a company on its, not company, a non-profit on its own, right? So we have certainly been part of those things. And, again, to some extent, if you actually think about even the routing problems that, Google Maps has commercialized now, I mean, you can go back, we were doing that research in 92 and 93. You can go look at our papers. And we had prototyped a Java-based, road maps and routing engine, well before even MapQuest came on the scene. So, it's up and depends on the interest, right? Somebody needs to take charge and commercialize it. Another example I will give you is evacuation planning. After Hurricane Katrina and so on, there was a lot of interest in the US to do that. And the local DOT used our algorithm to plan evacuations for twin cities. This was also used in Mecca, in Hajj, not far from where Sanjay is, to do emergency planning during Hajj for pedestrians, right? So there are lots of examples, and that's why the word use inspired, Sanjay used that word. I mean, we truly believe in use inspired. And we only start working on a problem when we see there is a real societal customer. Of course, our preference has been to work much more on societal problem, where the industry has not been, really interested very early. So we have worked a lot more with the government around, not only in US, around the world, to solve the problem society is facing.
Well, I would take some, you have the premise, the commercialization of research is the key. Well, you can question that a little bit. But yeah, I think, we want to, whenever we work on problems, we're always looking at, as Shashi was also mentioning, societal applications, use-inspired research, whether it's actually commercialized ultimately is, that's sometimes outside our ambit in some sense. But, a lot of it is serendipitous. So let me give you a concrete example. When we started working with a local taxi company here, the first problem that they wanted us to work on was, can you help us predict how many taxis should be at the airport at a given time? So they don't want taxis to wait at the airport for too long, but they also don't want passengers to have to wait for a taxi to arrive. There should be some taxi available there. And we tried to work on that problem for some time, and unfortunately, the heuristic that they had, we could not beat that heuristic. We used all kind of time series prediction, and somehow we just couldn't get good results, or not good enough results for them to change their system. So then, they were using. So there was a member in QCRI who said, okay, I have this taxi data, so maybe I'll try to come up with my own algorithm for ETA, estimated time arrival. And they said, oh, no, we are not interested in this because we already have a solution. We're using, Google Maps for that. And suddenly, next year, Google hiked their prices for that. And suddenly they came to us and said, okay, let's look at your solution. And then we were able to, adapt our solution. Because it was localized, obviously it did slightly better than Google's solution, and therefore now it's in some sense being used by the only taxi company in the country. So and then with this pandemic, there was a lot of demand. A lot of this food delivery companies popped up, and some of them are now using our technology from QCRI. For that. So I think, as I said, a lot of this is serendipitous, but if you have something good and something unique, hopefully you will find a user, a customer, or,
Just a quick remark that the going into industry and supporting industry applications in a stricter sense is not the only benefit, as we are aware. I was quite intentionally selecting samples from the NGO domain. So one of the great developments we are facing right now is that decision support is available to other institutions, to humanitarian organizations, other NGOs, in a way which otherwise and with traditional methods would not be possible, would not be affordable. So the hurdles certainly has been lowered quite a lot for those institutions as well.
We have also, our students have really helped the industry. So I don't know how many of you know Shiva Ravada. He's senior director at Oracle, and Oracle Spatial reports to him. He completed PhD with me, right? And he went there. We helped place it, right? I don't know. He's a well-known name in the space. I don't know how many of you know Jai Peng, another alum of UMN. He was chief scientist at DD Chuching, okay, trying to help them do this travel time estimation that Sanjay brought up, right? And Hui Xiong, another student of mine, was chief scientist as Baidu, which is Chinese Google, right? And at the end of the day, also remember that this space, your biggest customer is government. So don't delude yourself, whether it's Google Earth or ESRI. Look at biggest customers of ESRI. Number 1 customer, NGA. Number 3 customer, Army Geospatial Research Center, right? So this space, this is very different than advertisement-driven space of Facebook or Google, right? So don't kind of separate what government wants and what industry does. GPS came from government. Remote sensing came from government. I mean, we are in a space where this affects billions of people. You can't just separate, the industry and government and academia in this space. We all work together. So if you don't mind, I will, take the first crack. And around almost 8 years ago, I organized a workshop at US National Academies on behalf of Computing Community Consortium. This is an advocacy group of computer science within US. And they, bring all the sectors together. So this workshop, the government folks were there, number of, federal agencies, number of industry folks were there, and academic folks were there. The goal was to create a research agenda. And we did create that, which is what came out in Communications of the ACM cover article on spatial computing. And you can kind of see how it has influenced the federal research priorities. And also some of the companies have followed that, right? So in US, at least, I have been involved in science policy for more than 10 years now. And we don't see those lines. Everybody comes together and they bring different strengths, and we prioritize a research agenda. Some of that goes to White House and becomes a major research priority. Even the American AI initiative that you're looking at, CCC people were working on that for 5 years. So behind the scene, we are working together. And I hope the same thing happens worldwide. Every few years, we should come together, bring the best thoughts together, sort out what has been accomplished. Our field has done very well with GPS and spatial big data, and now we're doing well with remote sensing. But we need to look ahead and say, what are the next big compelling challenges, right? And then say, okay, this is the place everybody should bring their resources together. And we have different roles. Industry is driven by quarterly profit. So it's very well understood in the US and Britain that they do not have the capacity to solve hard problems and do long-term research. And that's the role of government. And that's why federal government creates these initiatives, right? You saw the DARPA and IARPA. Once the ideas have been sorted out, then academics and government, they are not very good at reducing cost and serving the customer. Then they hand it off to the industry and saying, okay, go take care of the customer, reduce the cost. Even Google, exactly same story. How many of you know that, the base technology of Google, PageRank, came out of an NSF project at Stanford, right? And they were student of Motwani, another friend of mine from IT Kanpur days. But then, ultimately they went and commercialized and they created jobs, right? And then they pay taxes, right? And that's the tax which helps the federal government fund research and pay tuition of our students, right? So these are not silos. We all need to come together. And in the US, this has happened very well for the last 20 years. And I can share because I have been in the thick of that. I'm still on Computing Research Association board. And I can share, all these things. Maybe we should do that worldwide. And that's the way to go forward. Thank you.
Yeah, so, just to, what synergies do you see between the broader AI community and global research, geospatial research community? The first thing, when I was doing my postdoc with Shashi, I learned that, something special about spatial data, right? That's so there is, you have to, when you apply AI to spatial problems, you need to look at the problem. What is unique about spatial data? And it still holds true that, when you, for example, if you take a first course in AI or machine learning or statistics, you start with this assumption, which is what data is identically and independently and identically distributed, and that immediately you have to, that assumption, you really have to relax when you seriously want to deal with spatial data. So I think so then you have to adapt AI machine learning research to the particular problem. So unless you work with each other, people will not realize that what is unique about the data when you work in geospatial or some other rich data type. So I think that's how it works. You look at the domain, you look at the problems, and then you try and work with people in the broader community, and then try and attract them to your area. And then this virtuous cycle is basically how gives rise to new technology, and then gets applied, and then and that's how it. I guess that's how it goes. So we have to be aware of each other, what's happening in the broader AI community, and also if you're interested in the geospatial community, and learn from each other.
Yeah, it's already been mentioned that it's all about communication. So whenever we work with people from these data science communities, from different subgroups in data science, we very quickly will realize when we exchange our experiences that such a large degree of their data sets, their experiences, is geolocated, has some spatial meaning to it. And they very quickly recognize that there is a lot of added value to be derived from making that explicit, to consider it and not just consider it nice. So in that sense, as long as we work together with our peers from the neighboring fields, that certainly will be a joint success.